بسم الله. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back in the general chemistry lectures. Inshallah, today we are going to complete chapter 10, which entitled with gas. And let me share with you the file I'm working from. Okay, Bismillah. Last time we have ended up with the Dalton's law. Okay, if you have a mixture of gases, the total pressure of the gases is given by the total number of mole in total times RT divided by V, and this comes from the summation of the partial pressure of different gases, okay, or the components of your mixture, and you can replace each partial pressure by this one, and you end up with this equation. And if you divide this one by this one, RT divided by V will cancel, and you will find P1 divided by P total equal to Ni or N1 say to say divided by N total, and Ni divided by N total is the mole fraction of the component I. So at the end of the day, the partial pressure of any component of the mixture is given by its mole fraction divided by times the total pressure of the mixture. Okay, now we are going to study the application of the Dalton's law, which is the collection of gases over water. Okay, suppose you have a reaction mixture here, which is done by heat, so to say, and the reaction is going to the right hand side to produce the products, and one of the products are gas, and it will be, this is a glassware which contain the reactants, and it should be closed by a stopper like that one, and the gas will flow from this tube, okay, and collected over the water. Okay, this is water. Okay, so here it's a mixture, it's a gas of interest, gas collection, and during the bubbles or the moving of the bubble of the gas, some of the water will evaporates, okay, water molecules. So here is a mixture of two gases, the water vapor and the gas of interest. Okay, so here the total pressure due to these two gases should be the partial pressure of vapor pressure of water plus the vapor pressure of the gas of interest. Okay, it's Dalton pressure. Okay, P total equal to the pressure of the gas and plus the vapor pressure of the water. When one, okay, just read with me that when one collects a gas over water, there is a water vapor mixed with the gas to find only the pressure of the desired gas, the gas under consideration, this one, it will be equal to the total pressure minus, okay, one must subtract the vapor pressure of the water from the total pressure. It's a direct application for the Dalton's law, okay, just to collect the gas over water, and you can calculate its pressure. Okay, this is a very good example. Okay, just I'm going to discuss it very not in details, just in brief with you, and you can study it, and if you find any problem, just contact me, and this also in the same book we are working from. Okay, automobile air bags are inflated by nitrogen gas. Okay, it's occupied by or filled by nitrogen gas by the rapid decomposition of sodium azide. Okay, this is sodium azide. Okay, this group, it's azide group, N3, it's a negative -1, it's a anion, it's called azide. Okay, this sodium azide, and this is a balanced equation. One of the product of the is nitrogen gas. Okay, I'm asking you if an airbag has a volume. Okay, this is the volume of the airbag or the volume of the gas, and is to be filled with nitrogen at 1.15 atmosphere. This is pressure. That's great. okay, and 26 degrees centigrade. This is temperature in Celsius. In Kelvin, it will be 207.3 plus 26. Great. And I'm asking how many grams of sodium. Okay, so I'm going to use the okay, data for the nitrogen, okay, to get the number of moles, so to say, from that equation of sodium oxide. This is balanced equation. So if you can calculate the number of moles according to these given data, you can calculate the number of moles and you end up with the number of grams. I'm asking how many grams. Okay, so just write the ideal gas law, BV equal nRT, which you have the pressure and you have volume and you have temperature, and the R is constant. It should be the value with the same units you are using for the other parameter. Okay, so you can calculate number of moles from here, and from the balanced chemical equation, it's 2 mole of sodium azide. Okay, 2 moles produce 3 moles of nitrogen gas. So if you take the N you got from here, okay, if you have N from here, sorry, N from here, it will give you X, say to say, which is the number of mole of sodium azide, and you can calculate the number of grams from the relation, which is that number of moles equal to the weight divided by the molecular weight. Okay, you have the molecular weight of sodium azide from the periodic table. Okay, 23 plus 3 times 14. Okay, and the weight which you are it's required to be calculated. You need to calculate it, and this N you got it from which is X. Okay, that's great. Okay, this is the plan. Just okay, gas data you have, you calculate the number of moles of nitrogen, and from equation you calculate the number of moles of sodium azide, and you end up with the number of grams of sodium azide. Okay, and so on. This is the in details solution of this equation. Okay. Okay, let us go to the kinetic molecular theory. What is kinetic molecular theory? It's theory, okay? And as I always telling you that any theory, it should contain some assumptions, okay? And these assumptions are true, okay? Are something like, it's true, like facts, say to say. Okay, actually, this kinetic molecular theory, it's a model which describes the behavior of gases, okay, and just okay, just what? Okay, I told you before, any gas has a pressure, and this pressure comes from the collision, or the main reason for the pressure, the collision of the gas molecules with the hole, okay, the border of the container. So the gas molecule exerts the pressure on the whole of the container. Okay, this model, which is kinetic molecular theory, gas kinetic molecular theory, this is a model that aids in our understanding of what happens, I wonder, that's very bad, this itch. Very bad. Okay, as I mentioned, this is a model that aids in our understanding of the behavior of gases, of what happens to gas particle as environmental conditional changes. We will see, okay? And this figure showed you the pressure of the gas is due to the collision of the gas molecule with the holes and so on. Okay. Any theory, as I mentioned, it has an assumptions, okay, or tenets, okay, something like, which is tenets, like assumptions, okay, or beliefs. Main tenets of kinetic molecular theory, or the main assumptions. The first assumption is gases consist of a large number of molecules that are in continuous random motion. Okay, gases are consist of a huge number of molecules which are in random motion in the container. Okay, the second one, the combined volume of all molecules of the gas is negligible related to or comparing to the total volume of the container. What does it mean that? As I mentioned, when we are starting, I told you in the beginning of this chapter, the real volume of a gas, it's something like, okay, 0.1% of the total volume. This is the real volume of the gas, of the total volume of the container, okay? Container. So it's a very, very small. That's what does it mean. Okay, if you have a container like that one, and if you collect the gas, it will be something like in this place, okay, which fill the whole volume of that one. So the real volume, this one can be neglected to the whole volume of the container. The combined volume of all molecules of the gas is negligible relative to or comparing to the total volume of the container. Okay. The third assumption, or the third tenets, the attractive and the repulsive or repulsion force between gases are negligible. What does it mean? It means there is no any attraction between the gas molecules and also no repulsion force. Okay, what does it mean? It means you could say that the collision it's quite elastic, no losing of energy, say to say. So there is no, and you could also say the intermolecular distance between the gas molecules are very, very huge. And that's why the attractive or repulsive or intermolecular forces, you could write that also. Intermolecular forces between the gas molecules are negligible. And also, as I mentioned, pressure inside the container comes from the collision of the gas molecule by the container. Okay, that's great. Okay, the second or the next assumption is energy can be transferred between molecules during collision. Okay, suppose you have two molecules which they are colliding together. Okay, suppose one lost energy, that amount of energy should be gained by the other one. Okay, that's why energy can be transferred during the collision, but the average kinetic energy of the molecule does not change. It's a constant. Okay, as the temperature is constant. So if this one lost an amount, it should be gained by this one. The average, the summation, it should be the same. Okay, that's why the average kinetic energy, as you see, are the same. You could find this is speed, molecular speed. Some molecules has lower speed, and some molecules has higher speeds, and so on. So, but at the end of the day, summation of all, okay, the kinetic energy, as you know, is given by, if you remember that, have mv squared. So it depends on the velocity, the speed. Okay, so the average, this average under the curve are constant. Okay, at constant temperature. If whatever, okay, even the collision is inelastic. What does it mean inelastic? It means, okay, one molecule lost an energy and that energy is gained by the other molecule and so on. Okay, that's agreed. Okay, the average kinetic energy of the molecule is proportional to the absolute temperature. Okay, the average kinetic energy, just reminding you, kinetic energy, say to say, is given by half mu or v squared. Okay, so the kinetic energy depends on the velocity, and this velocity depends on the temperature. When you increase the temperature, the velocity increases, so the kinetic energy increases. The kinetic energy of a molecule is proportional to the absolute temperature. Okay, just look to that diagram. You have to average kinetic energy of the gas at two different temperature, 0 Celsius and 100 Celsius, which is the red one. Okay, just if you are talking at that point, the speed here is this value. Okay, 500, say to say. Okay, if you look to the red curve, you will find at that line half of the molecule. Okay, this is half of the molecule have an speed larger than this value. Okay, if you go to the 0 Celsius, the blue curve, you will find that less than half. Actually, the half of the molecule should be at that line, but we are talking about here. So less than half of the molecule are of speed higher than that one. What does it mean? As I mentioned, as you increase the temperature, so if you increase another temperature, you will find the curve is something like that one. The average kinetic energy increase with increasing temperature, so to say 150 Celsius. Okay, so the average kinetic energy of the molecule is proportional to the temperature. As the temperature increases, the average kinetic energy increases because the speed of the molecules increases. Okay, let's discuss the application of the molecular kinetic theory. Okay, actually, a volume increase at constant temperature. As I mentioned, the constant temperature, so the average kinetic energy will be the same. So as volume increases, but at constant temperature, the average kinetic energy remains constant because it depends on the temperature. Okay, therefore, the speed is represented here by u. Okay, therefore u is constant. The speed, I mean. However, the volume increases. So the gas molecule have travel further to hit. Okay, if you increase the volume, the distance between, okay, or the distance by which the gas is exerted, so to say, or the distance the molecule moves, okay, or the molecules move to hit the wall or the wall of the container, okay, the distance increases. So the number of collision or the rate of collision with the container hole decreases. That's why the pressure decreases. At the end of the day, pressure decreases, and actually this is, as you know, Boyle's law. P or V is inversely proportional to what? To pressure. The volume increases, okay, the pressure decreases. Okay, it's inversely proportional. So if the temperature increases, as we mentioned, that the average kinetic energy depends on the temperature. If the temperature increases, the average kinetic energy of the gas molecule increases. Therefore, more collision with the container happens, so the pressure increases. Okay, now we're going to discuss new concept, which is diffusion, and at the same time, we will also discuss diffusion and effusion. If we will see what the difference between both. Okay, if you have a gas molecule and it moves in random motion, as you know, they collide the container and so on. Okay, if you start at that one and you end at that point, so this is the mean free path. Okay, in net distance traveled by, okay, the gas molecule. Okay, diffusion, its definition is the speed of the substance throughout space. Okay, if you have a gas molecule and it will diffuse in space, it's called diffusion. Speed of one substance throughout speed or throughout second substance. Okay, through a substance or a space. This is called diffusion. Okay, while effusion, it's escaping of gas molecule through a tiny hole, okay, into evacuated container. So effusion is escaping of a gas molecule through a tiny hole into evacuated space. Okay, evacuated space. Okay, that's great. So gas molecules in a top half of this cylinder, okay, effuse through a pinhole, this gap, this hole, okay, this pinhole through evacuated space. It's called effusion. While diffusion, it's spreading of one substance into space or into another substance. Okay. We are discussing, as I mentioned, the application of the kinetic molecular theory of gases. Okay, as the kinetic energy increases, as we mentioned, I told you that if the kinetic energy increases, the speed of the gas molecule, the velocity or speed of the gas molecules increases. And at a result, or as a consequence, the average kinetic energy also increases because the temperature is increases. Okay, the average kinetic energy, it's related to the mass and the velocity. Okay, this is epsilon, which is average kinetic energy, which half mu squared. I told you it's something like half mv squared is the same half mu squared, where u is the speed, the square root of this speed. Lower is the square root of this speed. Okay, consider two gases. If you have two gases at the same temperature, okay, and they are effused in each other, or diffusing to space, the lighter gas has higher root mean square heavier than the heavier one. Okay, what does it mean? Okay, if you would like to get the speed from here, okay, u, it will be something like square root of something, epsilon kinetic energy divided by m, and you end up with this equation. This is, it's called the square root. Root mean square. Root mean square of, okay, mean square mean speed. It means you have many molecules and they have different velocities, so you got the average or the mean. So that's what it's called, the mean. Okay, and root square, it's that one. So if you have two gases, according to this equation, the lighter gas will have will spread faster. Okay, will spread faster, and the average kinetic energy of it increases because the root mean square is inversely proportional to molar mass. As the molar mass increases, okay, the speed decreases. Okay, if you have two gases, okay, the lighter one has a higher root mean square value of the speed than the heavier one. Okay, it's a very, very important mathematical formula we are going to discuss later on, inshallah. Okay, this is example. Calculate the RMS speed of a molecule. It's a very, very important question. Okay, I'm asking to calculate the root mean square from that equation. Okay, it's very simple, but you have, okay, just direct application to this equation. But the molar mass here, it should be in kilogram. It should be in kilogram, not in atomic mass. It should be in kilogram, not in atomic mass. Okay. Okay, really? It's frozen? Okay, well, I don't know. That's great. And now it's working? Could you please tell me if it's working or not?
Yes, doctor.
It's working, Miss A? Does it work? Okay, don't worry. And now the same, or it's working? It should working. I have seen it's working.
Yes, doctor. It's working.
Could you please capture the question?
Thank you, Miss Ahdi. جزاكم الله خير. الله يحفظك. Okay, that's great. Okay, as I mentioned, you have seen this slide now. Okay, this is the average kinetic energy is given by this one. Okay, and you have two gases. The lighter one will diffuse faster than the heavier one, and the root mean square value, the root mean square value is given by this equation. Okay, it's directly proportional to the temperature and inversely proportional to the molar mass. As the molar mass increases, okay, as the molar mass increases, this parameter decreases. It's inversely proportional. Okay, this example, calculating the root mean square, okay, it's a direct application to this equation, but you have to keep in mind that the value of M should be in kilogram, not in atomic mass, okay? So you should use the conversion factor, which is 0.2, I think 1 point something times 10 to the power 27 kilograms C2C. Let's see. Okay, calculate the RMS speed of a molecule of nitrogen gas. I'm giving you the temperature. Okay, you should use that equation. The temperature should be in Kelvin, so you should add 273.15 to this value, and the R is constant. Okay, so the point is that we must convert each quantity into SI unit. And the SI unit of the R, it's 8.314 joule, something like that one. You remember that? Okay. And okay, the temperature and gram لكل مول. Sorry. Okay. In kilogram, sorry, in kilogram. Forget about this one. This one, if you convert from the atomic mass unit. Now, but while here I'm giving you the grams, you should just only times 10 to the power minus 3 to convert it to kilogram per mole. Okay, and the R it should be that one. Okay, so just direct substitution to this one, but as I mentioned, the molar mass should in kilogram, and you end up with the parameter you want to calculate. Okay, as I mentioned, the lower the molar mass, the higher RMS. Okay, you can look here. Okay, if you go in this direction, you will find the molar mass decreases. Okay, molar mass is decrease. Okay, this is oxygen, it's 32, nitrogen N2 it's 28, water it's 18, helium 4, hydrogen molecule 2. So the molar mass decreases. If you, as I mentioned, if you, for example, if you take at that one, for hydrogen, you will find most of molecules, say to say, its speed higher than this value, larger than this one. And if you look to oxygen, you will find a small amount of oxygen molecules, its speed larger than this one. As you see, as the molar mass decreases, the average kinetic energy, increases. Okay. And the average kinetic energy increases because the speed increases, RMS increases. That's great. Can you see that from the figure as I told you? Great. Okay, also this one, if you have two gases, and for example, if you have two balloons, one is filled with argon, okay, and the other filled with helium, and of course, this kind of balloons contain small holes, small pores, okay, small holes or small gaps, so to say, or hole. and the gas molecule escaping from it. You will find that at some time, you will find the rate of escaping of helium is higher than the rate of escaping of argon. Why? Because argon high molecular weight comparing to helium. Okay, this is 18. Okay, and this is just only 4. The molar mass is small, so its RMS is higher than the RMS of argon. The difference in the rates of effusion, that's great. Just I have already told you. The difference in the rate of effusion for helium and nitrogen, for example, explains why helium balloons would deflate very fast, because its molar mass, it's small. Okay. Also, application to the kinetic molecular theory, it's Graham's law of effusion. If you have two gases, as we mentioned, consider two gases with molar masses M1 and M2, okay, the relative rates of effusion is given by, okay, actually, the rate of effusion, rate of effusion is directly proportional to temperature. So it's directly proportional to the U, which it's called the rate mean square value of this speed. Okay, so if you have we have got from this one, if you have two gases and two rates, you have U1 and you have U2. If you divided them together, for the gas 1 and the gas 2, you will divide this something at the same temperature. This will be cancelled and you end up with that. Okay, M2 divided by M1. Okay, this is exactly the same equation here. Okay, as I mentioned, the rate of effusion is directly proportional to the U. So if you have two rates of two gases, R1 divided by R2, U1 by U2, you end up with this one, and this will be cancelled together, and you have M1 will be down in the denominator of the denominator, it's a numerator, so it's M1 divided by M2 divided by M1. Okay, so it should be something like, as I mentioned, R1 over R2 to give you M2 M1, because it's inversely proportional. Therefore, the higher the RMS, the more likelihood of the gas molecule hitting the hole. Okay, let's see this example. It's also an example. It's a direct application for the Graham's law. You have, but it has a good idea. An unknown gas composed of homonuclear diatomic. What does it mean? This is give you some hints. Homodiatomic. Okay, it should be two atoms. It could be, for example, like hydrogen, like nitrogen, like oxygen. Diatomic, homodiatomic. Homo, it means the same atom. Diatomic should be two atoms. Okay, if you use this at rate, this is the rate of its effusion times the rate of the oxygen. So you have the oxygen, rate of oxygen, rate of O2, and you have another rate of the unknown one. When suppose, for example, X2, its rate equals to that value of 0.355 of the rate of the oxygen. Okay, and I'm asking you calculate the molar mass of that one. It's a direct application to this. I'm giving you R1 to R2. Suppose this is oxygen, say to say, and this is the unknown one, X2. So this value I have already given you. It should be this one, the rate of oxygen to the rate, no, let oxygen downstairs, it should be downstairs, and here X2. Because I'm giving the rate of that one to the oxygen, so it should be this value, 0.355. And here, this is oxygen, it should be the molecular weight of the oxygen here, of O2, and the molecular weight here of the unknown gas. And the oxygen, it's okay, it's 32 divided by the unknown one, which is homo nuclear diatomic. Okay, so you have just only one equation which containing just only one unknown. You would get it easily, and after you get it, I'm asking for the molecular weight for what? Calculate the molar mass of the unknown and identify it. Okay, and just identify it. Okay, it's very simple. It's a direct application to that one, and I'm giving Rx to RO2, which is this value. Okay, if you for information, it's okay, should be oxygen up here and the unknown one. Okay, you end up with that. How can you identify it? I'm asking you that it's that homonuclear diatomic. You should divide this value by 2. You got the atomic weight for that element. If you divide this one, it will be 100 something, and it will be okay iodine. Okay, because we have told that the unknown gas is composed of homonuclear diatomic molecule, it must be an element. The molar mass must be twice of the atomic weight, as I mentioned. So you should divide that value by 2. You end up with the atomic weight of that element. You can identify it. This is an example comparing the here I'm asking you for the ratio directly. It's very simple. Okay, just Rn2 divided by RO2. It's equal to square root of O2, molar mass of O2, divided by molar mass of N2. I'm asking to get this one directly. Just you put. Okay, here I'm asking nitrogen to oxygen, so you should get the reciprocal of this equation. You can, it's okay. Okay, yeah, it's not reciprocal, it's the same. It's okay. I'm sorry, it's right directly. So it should be square root of 32 divided by square root of 28. So it will be higher than 1. Great. Okay, diffusion of the gas, the spread of the gas, something like summary. Here I'm summarizing what I have already told you. Diffusion of the gas, the spread of the gas through space. Okay, diffusion is faster than for light gas molecules. I mean, if you have two gases, the lighter one will have faster diffusion. Okay, diffusion significantly slower than the RMS. Okay, the diffusion is slower than the RMS, the speed, and this is normal. You could find that. Consider, for example, someone opening a perfume or perfume bottle. Okay, it takes some time to order it, to detect the odor. Takes some time. It takes a while to detect the odor, but the RMS, the speed of the molecule, it's very high. It's something like this value mile per hour. Okay, so the diffusion is slower than the RMS. Diffusion is slowed by gas molecule colliding. If you have gas and they collide with each other, okay, the diffusion will be small. The diffusion is slowed by gas molecule colliding with each other. Okay, this is summarizing for the most of the formulas we have already discussed in the gas chapter. Okay, you have the ideal gas equation, BV equals to nRT. Okay, and if you have two sets of gases, P1 V1 divided by N1 T1, B2 V2 N2 T2, and from this one you could derive all the gas equation, Boyle's, Charles, and Avogadro. And the application of that, you could calculate the molar mass or density from this relationship. Okay, and if this is Dalton's law, which is the total pressure of the mixture of gases. It's equal to summation of their partial pressures, P1, P2, okay, and where P1 is given by this one, just dividing this equation by okay, this one by this one, you end up with that the partial pressure of any gas, it's equal to its mole fraction, okay, its mole fraction times the total pressure, okay, and Graham's law of effusion, if the rates or the ratio of rates between two different gases is given by this one, where if one is here, it should be down here. 2, it should be, because it's inversely proportional to the molarness. Okay, the root mean square for the speed of the gas molecule is given by that one, U equals to square root of 3RT divided by M. And from this one, we can end up with this one if you have two gases. Okay, that's great. Okay, this is some revision. Let us discuss with us before taking the attendance. That's great. As a helium-filled balloon rises, okay, its volume increase. This is an example of what law? Yeah, Boyle's or Charles or what? Helium-filled balloon rises, okay, up. So the volume should be changed, say to say. I would say it should be volume and the pressure. I would suggest that. Which law that one should be Boyle's, say to say. B, that's great. Okay. We are discussing the relation between volume and pressure at constant amount and temperature, so it should be Boyle's. That's nice. Okay. Avogadro's law states that the volume of a sample of gas is proportional to what? Avogadro's volume divided, it's proportional to N, of course. Okay? Proportional to the amount of gas. Should be number of moles, of course, should be A. Okay, it should be A. That's great. The standard temperature and the pressure STP equals X atmosphere, should be X1 atmosphere, and Y it should be degree, which should be 0 Celsius. Okay, it could be okay, 0 Celsius equal to 173.15 Kelvin. Let's see which I'm giving you. X1, X0, no, it should be X1, it should be this one or this one. But I'm giving it temperature 0, it should be that one. So it should be B. This one will be right. You will take it when you are taking the physical chemistry one, inshallah, which is thermodynamic. The at SCTP, we're talking about thermodynamic, the temperature is 25 room temperature, not 0. But when we are talking about gases, the SCP the temperature is 0. Okay, so the right one should be here, B. Are you with me? Okay. Hello. A sample? Hello. Nobody answer me. Why? Where are
Hi,
you?
Doctor.
Everything is clear?
Yeah, Doctor.
Thank you, Miss عبد. ما فيش غير Miss عبد اللي معانا يا جدعان، جزاكم الله خيرا والله. Okay. A sample of 2 moles of nitrogen gas at SCTP. Okay, we have mentioned that SCTP means the pressure equal to 1 atom, and temperature, okay, temperature it will be in Kelvin 273.15. Okay, occupies a volume of liter. Here, okay, and I'm giving here N equal to. So I'm asking for the volume. So PV equal NR2 direct application, direct substitution in that one. You have the pressure, you have the N, you have R constant, but it should be with the same units. Okay, and temperature you have it, you can calculate the volume. It's a direct application, just no, it's without direct application. You needn't to do that. Of course, this one can calculate it, but you needn't. Okay, if you have 2 moles at SCTP, according to Avogadro's, okay, I'm sorry, According to Avogadro's 1 mole at SCTP, it's a volume 2.4, 1 mole. At SCTP, if I take 2 moles, okay, it will be double. It will be, as I mentioned, 448, say to say. Also, you can calculate it from here. It's no problem, but it's very easy, okay? Because you are at STP, Avogadro said that at STP 1 mole of any gas, its volume is 22.4. If you have 2 moles, just multiply this value by 2. Okay, so it should be that one. Should be that one. Okay, nice. A sample of 4 grams. Okay, this is weight of methane. It's a molecular weight 16, I think. Okay, okay, yes, 16 gas at SCTP. Okay, occupies a volume of. Okay, the volume of 1 mole. Volume of 1 mole, it's 2.4. And here I'm giving you the weight, which is 4. You can calculate the number of mole, which is 4 divided by 16, which is 124, say to say. It should be, just to divide this value by 4, it should be 5 something, I would say that. Just you have only here 5. Without any calculator, you can calculate it. A gas sample with a mass of, okay, I'm giving you the weight, I'm giving you here weight, occupies volume, okay, by milliliter at pressure, okay, by Joule, great, and temperature by Celsius, the gas is. Here I'm asking the gas, the identity of the gas. So you should calculate what the molar mass, okay? The molar mass, according to that equation, here, density RT divided by P. Density RT divided by P. Am I right? Where is it? Yes, density RT divided by P. This is the molar mass. Okay, so density, it should be weight per unit volume. I'm giving you here the weight, okay, but keep the track of the units. Okay, if you use gram per milliliter, it's a kilogram per kilo, it's no problem. So you should convert this one to grams, say to say, and divide by this one directly, and multiply with R. Temperature should be add to 173, and this should be converted to atmosphere. Okay, you should, okay, the pressure equal to 750 divided by 760 to convert to atom. Okay, and the volume, you need the volume here because you need the density, gram per mole, sorry, gram per milliliter. It's the same kilogram per liter. Okay, so you end up, you will find, okay, you have the pressure as I mentioned by this new value, temperature by that one plus 273, and the R, it should be 0.082 atom liter mole Kelvin. Okay, so you end up with the density, as I told you, density should be 88. Okay, so 10 to the power minus 3 to be gram divided by milliliter. So you end up with a gas, okay, from its molecular weight. Just you calculate the molecular weight for each one, and you end up, it will be carbon dioxide. It will be carbon dioxide. The partial pressure of each gas in a mixture of the gas, the partial pressure, which is Pi, okay, equal to mole fraction I times P2. Okay, a mixture of gas is proportional to the mole fraction. It's very simple. Okay, mole fraction. The kinetic molecular theory of gas states that the average kinetic energy of the gas particle is proportional to temperature. Okay, with closing your eyes, it's temperature. Okay, in Kelvin should be that one, by the way. Okay, this one is wrong. Neon gas undergoes effusion. El krypton. Neon, it's molar mass 10. Krypton, I think 36. Okay, I think. Okay, this one is lighter than this one, should be diffused faster. Okay, I would say that. Slower than, at the same, twice as fast as, 4 times as fast. Okay, this one or this one, it should be the same. It should be right. Okay, just to compare. If you divide that 33 by 10, it will be 3.6. 3.6, it's almost 4. So this is the right one. 4 times faster, as fast as. Why C? No, it shouldn't be C. Twice as fast as. I'm sorry. I'm sorry, شباب. Krypton xenon 36. Krypton 18. I'm sorry, 18. Okay, the molecular weight of the atomic weight of the krypton 18. So okay, if you divide, instead of this one, it should be 18 divided by 10. It will be 1.8, which equal to, okay, sorry for that. I'm sorry for that. So, as I mentioned, it should be krypton. Krypton what? It's krypton. It's not 18. Krypton, neon, argon. It's 18. Why? No. This one is wrong, Ishra. No. Krypton. Yeah, the molar mass of krypton is 83. How comes? Neon.
Yes, doctor. We are.
Okay, neon. And the krypton, it's 84, I think. 84, I don't think. No, the krypton is 36, as I mentioned. Okay. Oh. Sorry, Shabbat. Something is wrong here. Sorry. The molar mass of neon, it's 20. Okay, 20, not 20. 20. Okay. And krypton is 83 or 84. Okay, molar mass. Am I right? That's right, molar mass. Okay, so 84 divided by. So the right one is this one. This one it's solved wrong, Ashara. This one is wrong. D 4 times faster. This is the right one. Okay. The mean free pass. Okay, I told you the mean free pass, the distance between the starting one and okay, the total distance traveled by the gas molecule. No. The distance between the two gas molecules. No. Distance between the initial and the final should be the distance between a gas molecule and the container wall, the average distance traveled between molecular collision. Which one? The mean free path. We have already it, I don't know. The average distance. The average distance, so the mean free path, the average distance, which I showed you before. Where is it? We have discussed this one. Should be the net distance. Okay. Okay, I will tell you about that one later. No problem. It's okay. 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 Thanks God, we have already ended the chapter 10. اللهم لك الحمد. Thank you so much. Inshallah.